All right, subscribers, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is section 2.3, which deals with the reliability of measurements. So before we get going into these notes, there's a couple of objectives I want you to be able to meet by the end of this video. So objective number 1 is to define and compare accuracy and precision. Objective number 2, use significant figures and rounding to reflect the certainty of data. And objective number 3, use percent error to describe the accuracy of an experiment. Okay, so now we have to distinguish between accuracy and precision. So accuracy refers to how close a measured value is to an accepted value. And precision refers to how close a series of measurements are to one another. Now, the best way to distinguish accuracy and precision and see how they're correlated is by using these pictures. So these pictures here represent in the top left-hand corner something that's accurate. So they show an arrow right there in the center of the bullseye. Now, this next picture shows a precise set of arrows. They're all very close together, but they're nowhere near that bullseye. And then our third value, the bottom left-hand corner, shows a group of arrows that are all very close together, so they're precise, and they're in the center of the bullseye, so they're accurate. So they're both precise and accurate. And then the last picture here shows arrows all over the target, and that is neither precise nor accurate. Okay, so now we can get some real world data here, and this is some data of some students taking some trials on density of certain objects. So I'm going to ask you this: which student had the most precise measurement? So what we have to do is we have to look at the data. So student A had measurements of 1.4, 1.6, and 1.57. So each of these measurements varied by 0.06 of our measurement. Now student B here was kind of all over the place. They had values of 1.4, 1.68, and 1.45. So again, a couple of those were way off compared to others. That 1.68 is a way outlier, which means this student was not very precise. So then we look at student C, who had values of 1.70, 1.69, and 1.71. This is very, very close together. This is very close together, and because of that, student C is the most precise. Now, what I want you to identify from this set of data, what student was most accurate. And I should note this: the actual density from this set of data was 1.59 grams per centimeter cubed. So what we have to look at here is which one of these students had their average as close as possible to 1.59. So we look at the averages, and we see here student A with a value of 1.57 was very close to the actual density. So student A would be the most accurate. Okay, so that's how we can distinguish between precision and accuracy, and again, how they're interrelated and correlated to one another. Now with this data, what we can also do is talk about our percent error. So our percent error is broken into a couple of things. Number one, percent error expresses error as a percentage of the accepted value. And percent error is normally seen in a formula. And that formula is the percent error is equal to the absolute value of the error divided by the accepted value. And because it is a percent, we have to multiply what we just have here by 100. Now, I want to talk about this concept here known as the error. So error is defined as the difference between an experimental value and an accepted value. Now, error can be calculated with the following formula. And so our error can be calculated as follows. The error is equal to the experimental value minus the accepted value. Now, it's okay in your error to get a negative number, but remember, when you plug it into the percent error formula, the absolute value here takes away all negative numbers. So all numbers in our percent error will be positive. So let's go ahead, let's use this formula in an example on the next page. Okay, so right here it says calculate the percent error of all three of student A's measurements in this table below. So student A took 3 measurements in trials 1, 2, and 3, and they had the percent error already given to us. So the first thing that I want to identify is this. Our percent error formula that we're going to use throughout the entire problem here is as follows. The percent error is equal to the absolute value of the error, all divided by the accepted value times 100 to get us into percent. Okay, so we are going to use this formula in each of the trials. So we'll start out here with trial 1. So trial 1 gave us this. To calculate the percent error, we would take the error. We would take the error and we would put it in these absolute value lines. So we take negative 0.05 grams per cube centimeter. And we would divide it by the accepted value. Now the accepted value is 1.59 grams per cubic centimeters. And I'm going to write that down here. And so because that is the accepted value, we put this down here. And then we can multiply this by 100. Now, before we go to calculate, I want to consolidate some of these things, okay? So, absolute value bars. What those absolute value bars do is make no negatives. So, we have 0.05 grams per centimeter cubed divided by 1.59 grams per centimeter cubed. And then we multiply that by 100. So all we need to do is we need to get out our calculator. We need to get our calculator and take 0.05 divided by 1.59 times 100. So expressing this to 3 total digits, we'd have 3.14% error. And that was for trial number 1. Okay? So we're going to use the same type of concept, the same operations here to find our percent error in trial 2 and 3. So we start out here with trial 2. The percent error, and I'm going to save some space here, the percent error is equal to the error, which is given is 0.01. So we take the absolute value here of 0.01, so positive 0.01 grams per centimeter cubed, and we divide it by the accepted value, which is 1.59 grams per centimeter cubed. And then we multiply this by 100. Okay, so I'm going to consolidate here. This would just be 0.01 gram per centimeter cubed divided by 1.59 grams per centimeter cubed. Multiply that by 100, and we turn to our calculators. So we put in 0.01 divided by 1.59 times 100. To 3 total digits there, we would get 0.63. So the percent error for trial 2 is 0.63% error. And again, that was for trial 2. Now, the percent error for trial 3, very similar type of operations, just some different numbers. So to save some space here, I'm going to write trial 3. I'm going to draw an arrow here. We have the percent error equal to the absolute value of the error, which is negative 0.02 grams per cubic centimeters, all divided by the accepted value of 1.59 grams per cubic centimeters times 100. I'm going to consolidate this. Remember, the absolute value means that we have no negatives, so we have 0.02 grams per centimeter cubed divided by 1.59 grams per centimeter cubed times 100. Okay, so I'm going to plug this into my calculator. I'm going to take 0.02 divided by 1.59, and I'm going to multiply that by 100, and I get a percent error of 1.26%. So our trial 3 had a percent error of 1.26%. All right, so that's how we would calculate our percent error for each and every one of those trials. Okay, so now we can move into a little bit different topic, but it relates back to what we started this section on, and that was our precision. And so our precision can directly tie to this idea that we have as significant digits or significant figures. And significant digits are based upon the precision of available tools used for making measurements in the lab. Now, I should also note here that sometimes instead of using this significant digits, you'll see the term significant figures. Okay, so digits can be replaced by that term here of figures. Okay, now what happens here is that oftentimes in the lab, the precision itself is limited by those tools available or those measuring things that you have to use in the lab. And a simple example here of our precision being limited is clocks. And so if we have a digital clock what happens is it's only going to display the time to the nearest minute. Whereas an analog clock would display time to the nearest second with that second hand it has. And so because of these two facts here, the analog clock would be more precise than the digital clock. So a key takeaway from all of this is as follows. As scientists develop better measuring tools, the more precise their measurements can be. So sticking with our clock example, a stopwatch would be much more precise because it could measure to the nearest tenth or hundredth of a second. Okay, so we have this knowledge now that significant digits or significant figures are related to the precision of our measuring tool, but now we need to see this in actual application. So let's take this into example here of a measurement using a ruler. Okay, so with our significant digits and measurements, we have to know this. Significant figures, or digits, include all known digits plus one estimated digit. All right, so let's use that statement here about significant figures, and let's turn to this picture. So if we look at this picture, and it does a pretty good job blowing that image up, we know for sure that the measurement of this rod or stick is at least 5.2 centimeters. But the measurement doesn't quite get to 5.3 centimeters. So we can say, yes, this stick or this rod is at least 5.2 centimeters, but is not quite 5.3 centimeters. So we estimate one number past what we know. So again, we know for sure that we have at least a measurement of 5.2 centimeters. So when we make our estimation, this 0.03, that 3 there is an estimation. So if I write this down here as 5.2, and then I'm going to change colors here into this orange color here. This 3 is an unknown or an estimated digit here, okay? So I'm going to mark this here as our 3. Our 3 is the unknown or estimated digit. And for this reason right here, this is why we have significant digits and why we have to worry about it in science class. So again, we know for sure a certain measurement, and then we estimate one past that number to have an unknown digit. So everything has to have at least one unknown digit. Okay, so that is our basis for why we have significant digits. Now we're going to go over some rules and some examples for our significant digits or our significant figures. Okay, so for counting our significant digits, we have 5 rules that we need to follow. So rule number 1 is that non-zero numbers are always significant. So an example here is this. If we have the number as follows of 72.3 grams, we are going to have 3 significant digits. Because all of these are non-zero or numbers 1 through 9 numbers. Now, I should also note too that I may abbreviate significant digits as SF. So just kind of a side note here, if we have significant figures, I may abbreviate that as SF. We may use that in the future here. Okay, so that is rule number 1. Now, rule number 2 says zeros between non-zero numbers are always significant. So if we change this into an example or show this in an example, and we have the number 60.5 grams. This right here is going to have 3 significant digits. This 0, because it's squished in between a 1 through 9 number, is significant. So again, this would have 3 significant digits. Okay? Now, rule number 3 states all final zeros to the right of the decimal place are significant. So again, if we show this in an example here, if we have the number 6.20, because this 0 is after the decimal place, it would have 3 significant digits. Okay, we still have 2 more rules with our counting significant digits. And so we go to rule number 4. So rule number 4 says placeholder zeros are not significant. To remove the placeholder zeros, rewrite the number in scientific notation. So this rule sometimes is a little bit difficult. So I'm going to do 2 examples. So the first example is going to be the number 0.0253 grams. Now, these zeros out in front, they're called leading zeros. They are not significant. So right here, we only start counting at the 2. So we have 1, 2, 3 significant digits. Now, again, the problem said, or the rule said, hey, to eliminate all of this jazz, just rewrite the number in scientific notation. So if I take my calculator and I put 0.0253 and I press enter, and I convert this over to scientific notation by changing my form in the calculators, I could get 2.53 times 10 to the negative second. Now, when I do this in scientific notation, it should be noted that we only count the numbers in front of the times 10 to the power. Okay? So only when we're counting significant digits, only are the numbers out in front counted. Okay, our second example for rule number 4 is this. If we have the number 4,320, and this 0 again is a placeholder 0. And so this has 3 significant digits. Now, once more, we can eliminate this ambiguity, or we can eliminate this kind of question mark here by putting this number in scientific notation. So if I grab my calculator again, and I type in 4,320, and I convert this to scientific notation, I get the value of 4.32 times 10 to the third. And so again, it's really important to note this. We only count the numbers in front of the times 10 business. Okay, so we only count these numbers when we're counting significant digits. Again, the 2.53 and the 4.32. Okay, so that's how we eliminate that ambiguity of the rule number 4 here. All right, so rule number 5 with significant digits states that counting numbers and defined constants have an infinite number of significant figures. So examples of this would be something like 6 molecules, or a conversion factor that states 60 seconds equals 1 minute. Each of these things have an infinite number of significant digits. Okay, so we've learned our rules for counting significant digits. And I'll say this, they do not come naturally. It's something that we have to work on. But as we go through more and more practice, and we will do that together, it will come a little bit easier. Okay, so now we can talk about how we round off significant digits. Okay, so for rounding off of significant digits, the first thing that we need to know is this. Answers should not have more significant figures or digits than the original data with the fewest figures and should be rounded. Now, that's a lot to take in here, but another thing that should be noted is that when you punch these things, these numbers into your calculators aren't aware of these rounding rules that we have, or they're not aware of significant digits. You need to be the one that rounds it and puts the appropriate number of significant digits. Okay, so we're going to step into some more rules for rounding that we have in our rules about significant digits. So for rounding, we have 4 rules. Rule number 1, if the digit to the right of the last digit, if the digit to the right of the last significant digit is less than 5, do not change the last significant digit. So let's do a little example here. If we round the number 2.532 to 3 significant digits, we'll get as follows. Okay, so we want to round to 3 significant digits. So in this example here, 3 significant digits in our number is 1, 2, 3. So our last significant digit is 3. We look to the right. We say, hey, is this a 5 or less? It is. So when we round this, our answer would become 2.53. Okay? Now, our second rule states that if the digit to the right of the last significant figure is greater than 5, round up to the last significant figure, or round the last significant digit up. So let's try this in a little example. So if we want to round the number of 2.536 to 3 significant digits, we can apply this rule. So again, to 3 significant digits here, we have 2.53. We look to see if we need to round it by looking to that last significant digit, which is the 3. And we look here, we have a 6. It's greater than a 5. So when we say round to 3 significant digits for this number here, it would round up to 2.54. And that would be our answer. Now we have 2 more rules associated with rounding numbers. So our rule number 3 for rounding numbers is this. If the digits to the right of the last significant figure are a 5 followed by a non-zero digit, round up the last significant digit. So let's take rule 3 to an example. So if we have the following number, 2.5351, and I want you to round to 3 significant digits, we'll follow rule 3. So again, we identify, we want to round to 3 significant digits. We look to the right. We find a 5, but then we have to look to the right again. If it's anything but a 0, we round up. So looky here, we have a 5 and a 1. This means that the rounding here would be 2.54. Now the last rule is a little bit tricky. It's rule number 4, and it says if the digit to the right of the last significant digit is a 5 followed by a 0 or no other number at all, look at the last significant figure. If it is odd, round it up. If it is even, do not round it up. Okay, so there's a lot to rule 4 here. It's even sometimes confusing for myself to look at it, but let's take a couple of examples and round these numbers that I'm about to give you to 3 significant digits. Okay, so we start out here with example part A here. 2.53, those are 3 significant digits. We look to the right. It is a 5 and a 0. Now if it says, hey, this last significant digit, which is a 3, is an odd number, round up. Well, 3 is an odd number, so this would round to 2.54. Now let's look at a very close number here. We have 2.5250. We want to round it to 3 significant digits. Again, we have exactly 50, but we have to look at the last significant digit, which is a 2. So because that is a 2, it says do not round up. So this would become 2.52. Okay? I know these rules are a little bit confusing and a little bit tedious, but we will go through some practice that will help establish a little bit more comfortability using our significant digit rules. So let's go ahead, let's try an example out where we do round our significant digits. All right, so in our significant digits here, we are just going to round our significant digits here, or we're going to calculate the density of this particular object. So remember, density is D equals M divided by V. So our density is what we're trying to solve for. The problem does not give it to us. Our mass, if we read the problem here, it says the mass is 22.44 grams. And our V for volume is listed at 14.2 cubic centimeters. So all I'm going to do here is I am going to plug this into our problem. So we have 22.44 grams divided by 14.2 cubic centimeters. Okay, and I'm just going to put that into my calculator here, and we're going to go through this. So 22.44 divided by 14.2. All right, so like I said before, your calculator doesn't know how to round. It just spits out some digits here. So I'm going to write quite a number down. I'm going to write 5 decimals down. And so this value here would be 1.58028. Okay? And this would be in grams per cubic centimeters. And I'm going to ask you this. I want you to round to 3 significant digits. Okay, so 3 significant digits would get us this 1, 5, and 8. So we look to this number to see if we round. Again, the rule was if it is a greater than 5, we round up. If it's less than 5, we keep that number as the same. Well, 0 is less than 5, so rounding to 3 significant digits would get us a value of 1.58 grams per cubic centimeters. And again, that equals 3 sig figs, or 3 significant digits. Okay, so now I know a little bit more of our rules here, but we have to talk about addition and subtraction, and then we'll get to multiplication and division. So our rules for addition and subtraction in the relation to our significant digit is this. We need to round all numbers so that they have the same number of digits to the right of the decimal. And so to do this, I know that's kind of a broad statement. To do this, we have steps we can follow. So step 1 is to align all numbers on their decimal point and then add or subtract them. The second step is once these numbers are added or subtracted, any number to the right of the last significant digit will not be reported. Now, they may need to be there for rounding. All right, so I know this is additional rules that we have to think about here, but let's go through an example in our next page of notes. Okay, so our example says add the following measurements: 28.0 centimeters, 23.538 centimeters, and 25.68 centimeters. So the rules state here to be able to round when we do addition or subtraction, we need to line everything up on the decimal, okay? So what we're going to do here is we're going to put 28.0 centimeters, and then the next number, we're going to line up on the decimal, and we're going to draw our decimal. So 0.538, 23 is out in front, and then our last digit here, our last number, is 25.68. And so we would line it up as we have it written here. Again, I'm emphasizing here that we have the decimals all lined up in one straight line. So what we need to do is we just need to put these numbers exactly as we see it in our calculator. So all I'm going to do here is I'm going to take 28.0 plus 23.56 or 538, excuse me, 538 plus 25.68. And I press enter. Now I'm going to write down everything that I have in my calculator. So I have 77.218. Okay? Now I'm going to adjust this, and I'll tell you why I need to adjust this here in just a second. But I'm going to rewrite the decimal numbers. So I have 0.218 centimeters. Okay? Now, the rule said, hey, the last or the number with the least amount of decimal places in it, that's what we need to round to. So check this out, 28.0, it's only having one digit after the decimal. So what you do here is if you draw a dotted line to that number with the least amount of significant digits, that tells us what needs to be reported in our answer. So when we would do this, we would look at 2 being our last significant digit. We would ask ourselves, would a 1 make the 2 round up? The answer is no. So our answer, rounded to the correct number of significant digits, would be 77.2 centimeters. And that becomes our answer. Okay? All right, so one more set of rules, and that applies to significant digits and multiplication and division. This one's a little bit simpler. Hopefully you'll like it. But for multiplication and divisions, we just need to round the answer to the same number of significant digit as the original measurement with the fewest significant digits. Okay, so that's all the steps that we need to do, and I can show you how this works in an example. So if we transition here to this, it says calculate the volume of a rectangular block with the following dimensions: a length of 3.65 centimeters, a width of 3.20 centimeters, and a height of 2.05 centimeters. Okay, so what we need to do is we need to just calculate our values that we have in our given set of problems. Okay, so volume, remember, is length times width times height. So our volume in this case would be our length of 3.65 centimeters times our width of 3.20 centimeters times our height, which is 2.05 centimeters. Okay, so all I'm going to do is multiply these numbers to find out our volume, and I'm not going to do any rounding right now. All right, so I get a value of 23.944, and again, this is not rounded. That would be cube centimeters if you're worried about units, but now we have to worry about rounding. So we ask ourselves, the rule said, hey, look at the original values, and whatever number has the smallest number of significant digits, that number of significant digits needs to appear in your answer. So right here, for our length, we had 1, 2, 3 significant digits. And I'm going to abbreviate that as SF, so 3 significant figures. Over here, we ask ourselves here, we have 1, 2, and the question becomes, do we count the 0? Yes, we count the 0 because it is after a decimal and you've had a non-zero number. So this guy right here also has 3 significant figures or 3 significant digits. And then we get to 2.05. Now, 2.05 has 1. We ask ourselves, do we count the 0? Yeah, it's smushed in between 2 non-zero numbers. And we also count the 5. So this would have a value of 3 significant figures. Now, I made it real easy on you because that means if every number in our given quantities had 3 significant figures, our value here has to have 3 significant figures, or 3 significant digits. So we have 1, 2, 3. We ask ourselves, does a 4 make the 9 round? The answer is no. So rounding our volume to 3 significant figures, or the correct significant digits, would give us a value of 23.9 cubic centimeters. All right, I threw a lot at you with the significant digits. It's not something that comes naturally to people, so we'll work on it time and time again, and we will have additional practice as well as homework. All right, so this has been a lot in this episode. I hope you have enjoyed it, and as always, if you have not already, make sure you subscribe.